Alright, in this video we are looking at solving inequalities. Now, for the most part, as long as the inequalities are linear, you just solve them as you would solve regular equations, except if you end up multiplying or dividing by a negative. So if we look at this first guy right here, 2x minus 17 is greater than 51. We've got to get the x by itself, so we need to add 17 to both sides. So we have 2x is greater than 68, and we finish getting x by itself by dividing both sides by 2. So x is greater than 34. Now the instructions say to give the solution set using interval notation. Now a lot of times what you may do is draw a graph. There's not really much to do in the graph here on this guy. The only number you care about is 34. I would put an open circle at 34. X representing the solutions would be greater than, so that's out to the right. Remember, we're using open circle because we're not including 34, because x's are only greater than, but not equal to 34. The interval notation from the number line will be from 34 to infinity. Now remember, we always use parentheses unless there's an endpoint that we include, and then we would use a bracket. So in number 2, I need to get the x by itself, so I need to move the 9 to the other side. So when I subtract 9 to the other side, that's going to give me 27. And here I need to divide both sides by negative 3. And when I divide by negative 3, that's going to turn the inequality from being greater than to being less than or equal to. And so 27 divided by negative 3 is negative 9. If you were to graph this, and again, you don't have to do the graphs if you don't want to. This is negative 9. I'm equal to negative 9, so I'm going to have a closed circle, including that guy. And less than, so it's going to be out to the left. So the interval notation for this will be from left to right. It's always left to right. That's from negative infinity to negative 9. Since I am including the negative 9, we'll put a bracket on that. So in the last example, it was an open circle because I was not including the 34, so it had parentheses. I am including negative 9, so it gets a bracket. Now, number 3 is what we call a compound inequality, and more specifically, it's a 3-part inequality. Your goal is to get x by itself. So if I had just this inequality right here, you would add 19 to both sides, like this. But we must keep in mind that it's not just that inequality. It's also this inequality as well. So if I add 19 here, I must also add 19 here. So this gives me 5 is less than x is less than or equal to 123. If I were to look at this on a number line, you see that my solutions will be everything that's in between 5 and 123. You are less than or equal to 123, and you are greater than 5. So that would include all of the numbers in between, and since it's equal to 123, I get to fill this in. I'm not equal to 5, so it stays open. And then the interval notation would be parentheses on the 5 to 123, and this guy gets a bracket because I'm including the 123. Now you have another situation just like number 3 here in number 4. In number 4, you still want to get the x by itself, so you need to move the 7 first. So subtract 7 off of everything. This gives us 8 is less than or equal to negative 2x. Don't forget about your signs. And that's less than or equal to 24. Then we divide everything by this coefficient, which is negative 2. And this is where you need to be careful. You are dividing by a negative, so the inequality symbol is going to change around. Instead of being less than or equal to, it now becomes greater than or equal to. This is just x, and then we have greater than or equal to negative 12. Notice that x is in between these guys, but sometimes it gets kind of confusing to read this. You have to make sure you are going from left to right, especially when we get to the number line. So sometimes we may rewrite this and say negative 12 is less than or equal to x, which is less than or equal to negative 4. Notice that the inequality implications still go the same way. Negative 4 is greater than negative 12. Negative 12 is less than negative 4. So it all makes sense. If I were to graph this, I have from negative 12 to negative 4. Now, had I not rewritten it this way right here, it might be very tempting to say negative 4 is on the left and negative 12 is on the right. But according to the order of the real numbers, it doesn't make any sense to have it flipped around. X is between these numbers, so I'm including both of these. Excuse me, I'm including everything in between, and since I do have the equal to, both of these guys get filled in. So my interval notation will be bracket on the negative 12 to negative 4, and that guy also gets a bracket. So these inequalities really are not that bad. We've been seeing these for a long time. It's the next inequalities that are kind of difficult. So look here at number 5. Number 5 is a quadratic inequality. Now what we do here is we're trying to find those critical values. So I'm going to do this just the way that I showed you in class. First, you want to factor this guy. So factoring is something that we've been taking care of for a while. So you should be able to factor this guy as 2x and x. Watch your signs. 14 breaks down as 7 times 2. And a quick inspection will show you that you get a negative 7x here in the middle, negative 4x on the outside, and that's a negative 11x altogether. Now we want this guy to be greater than or equal to 0. A temptation here is to try to set each of these factors to be greater than or equal to 0, as though you're using some kind of zero factor theorem, but it doesn't work that way. Looking at these guys right here, we want to identify critical values. These factors can identify to us our gatekeepers, these critical values where you have the potential to go from a positive to a negative or vice versa. So what makes this guy equal to 0? 7 halves. And the other guy here is x equals positive 2. These are the critical values that will separate my number line into distinct sections, and then I would check to see which ones are true, false, positive, negative, and all that jazz. Now, this is the way I like to do this. I like to use a sign chart, like this. So I list each of my individual factors, and then I write the expression in its factor form below it. And then I draw my number line with my critical values indicated. Now make sure that you put these in the correct order. 7 halves is really 3.5, so that's larger than 2. So 2 is on the left, 7 halves is on the right. So we create this little chart just like this. Because here's the thing. 2x minus 7 is 0 at x is 7 halves. If you pick a number on the left side of 7 halves, say something like 2, and you plug it in here, 2 times 2 minus 7 is negative. If you were to pick 0, 2 times 0 minus 7 is negative. It doesn't matter what number you pick on this side of 7 halves. This factor will always be a negative. And if you pick something on the right side of 7 halves, this factor right here is always going to be positive. So I don't need to know what the exact number is if I do a test point. I just need to know what the sign is. That is the only thing that's important to me. Now here, x minus 2 is 0 when x is 2. So this is his gatekeeper. And on the left side, since this guy's a positive lead coefficient, he's negative, and on the right side, he's positive. If you don't believe me, pick numbers on either side of 2, and you're going to see that on the left side it's negative, on the right side this factor is positive. Now, the key thing is going back to the original inequality. We have this guy factored and see how it compares to 0. We want it to be greater than or equal to 0. Well, negative times negative gives me a positive. Because see, that's what these factors are doing. They're multiplying. Negative times 0 is 0. Negative times positive is negative. 0 times positive is 0. And positive times positive is positive. So the question here wants to know, when are you greater than or equal to 0? That corresponds to having positive numbers like what we have here. And see, it doesn't matter what the numbers are as long as they're positive. So that means in terms of my number line, anything to the left of 2 will give me a positive value, which is going to make it greater than 0. Anything to the right of 7 halves also gives me a positive value. But the other part of the inequality says you can also be equal to 0. So that means I get to include being equal to 0, which happens at these values, 2 and 7 halves. So here's my number line. My inequality will go from negative infinity, or my interval notation, negative infinity to 2 with a bracket. Union, we use that union symbol to join this section with this section. It's going to be from 7 halves to positive infinity. Now, one of the things that you can see here is what this looks like on a graph. So let's check that out real quick. If I were to graph this original inequality, which is 2x squared minus 11x plus 14. And there's the graph. What you will see here is that we're trying to find out where's this guy greater than or equal to 0, meaning where is he above the x-axis. This parabola is above the x-axis here on the left side, and then again here on the right side. Well, what are those numbers? Well, that's what we got whenever we factored, and you see these numbers match up with positive 2 and the 7 halves. Now here's something else that you can do with the calculator. You can actually have it graph the solution set as long as you understand how to speak computer. If I go back to y equals, I can actually type in the inequality and have it graph the inequality. To get to inequalities, you have to go to this test. So you have to press second math to get to test. Now, this says greater than or equal to 0, so greater than or equal to is option number 4. Now, what the calculator is going to do is it's going to not graph this the way you expect it to. This right here is it's either going to be true or false. This guy's either going to be greater than or equal to 0, which is true, or it's going to be false. Now, if it's true, the calculator will graph a 1. If it's false, it graphs a 0. Let me show you what I mean. See how it has this little line here? This is when y equals 1. So this is when it's true. It's not up here at 1, so this is false, and then it's true again. If we change the window, you can see this a little bit better. Change the y min from 0, or to 0, and change the y max to 2. And we're going to pause the graph for just a second. You see going from 0 to 2, so you can clearly see when it's going across, here's when the values are true. And when it dipped down right here, that's when it was false. It dipped down to 0. So this does match up with this number line that I have graphed here, because it's going from 2 to the left. Mine's going from 2 to the left. This is going from 7 halves to the right, and this is also going from 7 halves or 3½ to the right. So that's your solution set. You can actually see it, graph it. Now let's take a look at a rational inequality. A rational inequality works the same way as a quadratic inequality. You just have to see everything in terms of its factors. So in number 6, I can't compare it to 2. That makes it very difficult. Instead, what I do is I need to have this set equal to 0. So bring the 2 over by subtracting it. And now you want to get this guy to be one single fraction. That way you can clearly see what all the factors are. So we see here that this guy needs the factor of x minus 3 in both the numerator and denominator. So we have x minus 3, and in the numerator we'd have x plus 2 minus 2x plus 6. And all of this is less than 0. Combine like terms. We have negative x plus 8 over x minus 3. And this is where we start finding what are the critical values. Let's see. The critical values are what would make the numerator or denominator 0. So what makes the numerator 0, if I look at this, if you had to solve this for x, or solve this equal to 0, you find out that the critical value is x equals 8. And the other guy is x equals positive 3. Okay. So we're going to do a sign table just like we did before, but it's going to be a little bit different because of the factors that we have. So one factor is negative x plus 8. The other factor is x minus 3. And then we look at what happens whenever I take this as a division problem. Okay, and then here is my number line. My critical values are already indicated to be 3 and 8. So we're just going to create our sign chart here. So here's the thing. Negative x plus 8 is 0 when x is 8. If you pick numbers to the left, it won't actually be negative. Since this guy leads with a negative coefficient, it's actually going to be positive over here. It's the opposite of what you would expect. If you don't believe me, pick numbers. If you were to pick 3, negative 3 plus 8 is positive. Pick 0 over here. Negative 0 plus 8 is still positive. So you have all these positive numbers on the left. If you pick numbers greater than 8, say 9 and 10, negative times 9 plus 8 is negative. So they're negative on the right. Now the factor x minus 3, who has a 0 here when x is 3, he has a positive lead coefficient, so he's going to be just what we saw in the last problem. Negatives on the left, positives on the right. It's when we get down here that we have to be very careful. See, this is division. Positive divided by negative is negative. Positive divided by 0, however, is not 0. When you divide by 0, you are undefined. This is very important for us to notice that. Positive divided by positive is positive. 0 divided by positive is 0. Negative over positive is negative. So our question here is wanting to know, when is this expression less than 0? So to be less than 0, we need negative values like we have here. So on the number line, that's going to correspond to everything that's to the left of 3 and everything that's to the right of 8. But do I get to include these points? Do I get to include 3? Well, since this is undefined, you would never be able to include that. Now this is equal to 0. This inequality does not give you the option of being equal to 0. It's just less than. So this guy must remain open as well. Had this been equal to, the 8 would have been filled in. But the 3 would still have been open because it's undefined. So in terms of the interval notation, we are going from negative infinity to 3, union, and then 8 to infinity. Parentheses all around. Now you can take this original inequality and check this in your graphing calculator. So, for the y equals, we're just going to type in this inequality. So be careful with your parentheses. So we have parentheses, x plus 2, close parentheses. This is all divided by x minus 3. And I want to know, when is this guy less than 2? So go back to your second math, so your test menu. Less than is option 5. When is that less than 2? Now, we are saying that it's less than 3 and greater than 8. Let's see if the graph agrees with us. So here it is coming over here, that's less than 3. See how it drops down here at 3? And it should pick back up again here at 8. And there it is. That's the exact same thing that I see with my, try to get this on here for you. It's the same thing that I see with my interval notation with the graph. Less than 3, greater than 8, less than 3, and greater than 8.